In this video, we will continue our investigation into improper integrals. So an improper integral of the first type is one with an infinite interval of integration. For example, if you're integrating from a to infinity, how we handle this is by rewriting in terms of a limit as t goes to infinity, definite integral from a to t. From a procedural aspect, you write as a limit, evaluate the definite integral, and then take a limit of that result. Let's investigate one additional example. So immediately upon inspection of the limits of integration, this is an improper integral of the first type. So we write it as a limit. The limit as a approaches infinity, the integral from 0 to a of e to the x over e to the 2x plus 3. And as this is familiar to integrals we've previously evaluated, I'm going to immediately rewrite e to the 2x as e to the x squared. And hopefully rewriting that as e to the x quantity squared gives you a hint as to the method of integration we are going to use. We will let u be equal to e to the x so that du is e to the x dx. So e to the x dx is our du, and e to the x is u. So at each step we write down the limit, so limit as a approaches infinity. An integral with limits of integration we are going to need to determine, but the integrand very conveniently becomes 1 over u squared plus 3 du. For the limits of integration, we will use our substitution. So when x is equal to 0, u is equal to e to the 0, which is 1. For the upper limit of integration, when x is equal to a, u is equal to e to the a. And that gives us the upper limit of integration. Now in terms of evaluating the integral, we do need to remember a familiar integration formula from the previous chapter. So let me recall this to the side. If you want to integrate 1 over x squared plus a squared, there is an associated arctangent formula. It is 1 over a arctan x over a plus c. So upon inspection, our a would be the square root of 3. So putting this together, we have the limit as a approaches infinity. And if we use our formula with a equals the square root of 3, this will be 1 over the square root of 3, arctangent of u divided by the square root of 3, and we are evaluating from 1 to e to the a. So we plug in u equals e to the a, put a minus sign, plug in u equals 1. So that would be 1 over root 3 arctangent of e to the a over square root 3 minus 1 over root 3 arctangent of 1 over root 3. And keep in mind that whenever possible, we should always evaluate common values of trig and inverse trig functions. And the common value in this example is that arctangent of 1 over root 3 is equal to pi over 6, because the tangent of pi over 6 is 1 over root 3. So now we go ahead and we evaluate the limit. So as a goes to infinity, we have e to the a itself going to infinity. And if what's inside the arctangent is going to infinity, that means that the arctangent itself would be going to pi over 2. So putting this all together, we have 1 over root 3. Then we have the limit as a goes to infinity of the arctangent e to the a over root 3 is pi over 2. And then we're subtracting away 1 over root 3 pi over 6 because the limit of a constant is that constant. So you have a 1 over root 3 that pulls out of both terms, and pi over 2 minus pi over 6 is pi over 3. And this number is the value for this improper integral. And hopefully what this example illustrates for us is that they can be a bit more involved. There's quite a bit of work that takes place. Once you rewrite it as a limit of a definite integral, any of the techniques of integration we've encountered in the past are certainly fair game. Substitutions, integration by parts, etc. So let's look at one more motivating example. So note that we're integrating from 0 to 2. So this is not an improper integral of the first type. But it turns out if we think about the function we are integrating on this interval, the function is undefined at 2, and this is going to result in an improper integral of the second type. So let's just see if we can work our way through this intuitively. So if I consider a graph of our function, so we're thinking f of x equals 1 over the square root of 4 minus x squared. So if we think about what's happening between 0 and 2, when you plug in 0, you end up with 1 over the square root of 4, which is going to be 1 over 2, so 1/2. And then as you plug in numbers getting closer to 2, you're going to be dividing by something smaller. And in fact, as you get really close to 2, you're dividing by something really small, which means it's approaching infinity. So the graph is going to have a vertical asymptote at x equals 2, and roughly speaking look something like this. So in terms of evaluating the integral from 0 to 2, because the function is undefined at 2, we cannot apply the fundamental theorem of calculus. But what we can do is rewrite it, much like we did with the first type of improper integrals, as a limit. So what we can do is evaluate the integral from 0 to, let's say, t, where in this case t is going to be some number a little bit to the left of 2. So what we want to do is think about taking that t and letting it approach 2. So we'll need to take the limit as t approaches 2 from the left-hand side. And this is going to be something that we refer to as an improper integral of the second type. So if we go ahead and evaluate the integral, this is a convenient integral for us to evaluate. We'll have the limit as t approaches 2 from the left, and the value of this antiderivative, because it's of the form 1 over the square root of a squared minus x squared. So this 4 is 2 squared. This is going to be the arcsine of x over 2, another of our common anti-differentiation formulas. And we're evaluating from 0 to t. So we have the limit as t approaches 2 from the left of arcsine of t over 2 minus the arcsine of 0. Recall that the arcsine of 0 is equal to 0, so that term vanishes. And what remains is really evaluating the first part of the limit. So as t approaches 2 from the left, this t over 2, the thing that's inside the arcsine, is approaching 1. And the arcsine is a continuous function, so this limit will be the arcsine of 1, which is pi over 2. And this value pi over 2 is the value of this improper integral. And note geometrically what it corresponds to would be the area enclosed between our curve and the x-axis from x equals 0 to x equals 2. Just to recap, we've seen our first example of an improper integral of the second type. So for an improper integral of the second type, we're going to have an example where we are integrating a function from a to b, But as we approach b, the function is either going to plus or minus infinity. So maybe like in this previous example, it was something like this. So in this case, because of this infinite discontinuity at x equals b, what we need to do is write it as a limit. So instead of integrating from a to b, we'll think of integrating from a to some number t, and we'll need to let t approach b from the left. And drawing the picture, much like we've done here, will always help remind you what direction we need to approach from. Now note, we similarly could have had that infinite discontinuity at the left-hand endpoint instead of the right-hand endpoint. So if we draw a corresponding picture, so say we're integrating from b to c, and our function has an infinite discontinuity at b. So graphically, it could look, something like this. So now what we'll do is say, well, we cannot integrate all at once from b to c, but what we could do is specify a value of t just a little bit to the right of p. And then we would need to take that limit where we have the value of t approach b from the right-hand side. So the idea is very similar to improper integrals of the first type, with one subtle twist. We somehow have to recognize that even though we have these finite limits of integration, you have some type of infinite discontinuity, which makes it an improper integral of the second type.